So we're gonna look at chapter 12. So I'm gonna turn to chapter 12 in your packet. It says chapter 12, goodness of fit test. So the first thing before we get into the tests is we're gonna introduce a new type of distribution. So we had the normal distribution, which we used for the one prophecy test when we're doing proportions. And then we have this t distribution that we use for means. Okay, when we're dealing with categorical data, which is another name for qualitative data, we use a different distribution to figure out the probabilities. It's called a chi-squared distribution. And we use the test statistic for the chi-square distribution is the chi-square statistic, which looks like this. It's like a cursive X, which is chi, the Greek letter chi, and then squared. So chi-square distributions, like t distributions, have many different shapes, or they look different based on the degrees of freedom. And the degrees of freedom is always how many categories you have minus one. So if you have two categories, you have 1 degrees of freedom, and it looks like this blue line. And we don't usually have just 2 categories, we usually have more. If we have 5 degrees of freedom, it looks like this red line of the chi-squared curve. 10 degrees is this green. 20 degrees of freedom is this purple. And if you have 30 degrees of freedom, it's this black line. And as you can see, as the degrees of freedom get bigger, it starts to look more and more like a normal distribution. It's not as high, like the peak is not as high. But for smaller degrees of freedom and in general, chi distributions are skewed to the right. Even this one is slightly skewed to the right. And the chi-squared statistic is always greater than or equal to 0. They're never negative. Kind of different than more like a z score, which is the test statistic for proportions, can be negative, and the t-score can be negative. So we use chi-squared alpha to represent the value that has an area of alpha to its right. And we can use a table to find the critical values using the chi-square distribution. Now, we will not use a table. We'll do everything in our calculator. If you have an older calculator, you will have to find the chi-squared statistic. And to do that, we'll use the chi-squared CDF command. It is the same place as the normal CDF. So if you hit second distribution and then scroll down, it's number 8, the chi-squared CDF. That will help us find the probability of being greater than this, which will give me the p-value. And it's always to the right. Like we're always finding the probability to the right when we do these chi-square distributions. So the first test we're going to look at is called a chi-square goodness of fit test. And this is not in your packet, but just a little bit of background. So chi-square goodness of fit tests are statistical tests aiming to determine whether observed values match what is expected. So we're going to have a contingency table involving categorical variables. And the question is how well does the actual data fit some known or theoretical distribution? So one example would be if you roll a 6-sided die like 100 times, do you get what you would expect based on the theoretical distribution that when you roll a die, all of the numbers should come up equal number of times. So it should be uniform. Uniform means that they're all equal. So I should get the same number of 1s, 2s, 3s, 4s, 5s, 6, because we know that the probability of each number is 1 out of 6. So does that actually happen? Another common use of this statistic is when you look at packages of Skittles or M&Ms and say, does the color distribution that you get in a package of M&Ms actually meet with what they say? So we said that Mars said that there should be 24% blue M&Ms. When we open our package of M&Ms, do we actually have 24% of them being blue? Okay. So that's what we're going to look at, that type of test. So just what it's gonna look like is something like this, where, for example, a shop owner thinks that people's ice cream flavors are reflected by the following model, like 25% are vanilla, 25% are chocolate, 20% are strawberry, 15% are butter pecan, 8% Rocky Road, and 7% are no preference. And so that's what the theoretical is. That's what we believe to be true. Then we take a random sample of 1,000 and they get the actual account. We get 220 vanilla, 255 chocolate, 190 strawberry, 170 butter pecan, 95 Rocky Road, and 70 no preference. Okay, so those are the observed values from the survey. So when we're looking at these problems, we're going to make a table each time comparing the observed and the expected. So the observed is the counts we get from the sample. We know there's 220 vanilla, 255 chocolate, 190 strawberry, 170 butter pecan, 95 Rocky Road, and 70 no preference. Okay, that's what we observed. We want to say, okay, what is expected based on the believed percentages? So if I have 1,000 people, or a sample of 1,000, and 25% are vanilla, how many should actually be vanilla? So to find that, we always take the percentage and multiply by the sample size to get how many. So I take like 0.25 times 1,000. And that gives me 250. And then I would do the same thing for every category. So for chocolate, it was 25% again. I would take 0.25 times 1,000 again, which would give me 250. For strawberry, it's 20%. So I put 0.20 times 1,000, and that would give me 200. For butter pecan, it was 15%. So I take 15% of 1,000, and we get 150. We have 8% Rocky Road, so I would take 0.08 times 1,000, and that would give me 80, should have been Rocky Road. And no preference was 7%, so I take 0.07 times 1,000, and I would get 70. And so we get our expected counts, which is based on 1,000 people, and the believed percentages, how many should fit each category. And so the chi-squared goodness of fit test is going to measure like the difference between the observed and expected and figure out what is the probability of getting this expected that we actually got, assuming that they should have been equal. That it should have met what we had. Okay, so for this, when we write our hypotheses, what we generally say is the distribution of counts of blank occurs in a manner consistent with the model provided. So what we expected matches what we observed, or what we observed, I should say, matches what we expected. The alternative hypothesis is the counts does not match. So the distribution of counts of blank occurs in a manner that is inconsistent with the model provided. So in this case, the one I just looked at, the distribution of counts of ice cream occurs in a manner consistent with the model provided. The distribution of counts of ice cream occurs in a manner that is not consistent with the model provided. Now, there's one on Alex. They kind of explain the null and alternative hypothesis differently. And the way they do it only works if the probabilities are equal. So if all the probabilities are equal, which they might say uniform, because uniform, remember, meant that like all the heights of the bars were the same. You could write the hypothesis in this way. You could write that the probability of the first equals the probability of second equals the probability of however many you have equals whatever that probability is. And the alternative is one of the probabilities are not equal to it. You can't say all of them are not equal, it's just one of them does not match that. So, for example, if we're talking about rolling a die, we know that the probability of rolling a 1 is equal to 1 out of 6, and the probability of rolling a 2 is 1 out of 6, and rolling a 3 is 1 out of 6. Like we talked about that when we did probability. So we could write that null hypothesis as P1 equals P2 equals P3 equals P4 equals P5 equals P6 equals 1 out of 6. And then the alternative would be one of the probabilities does not equal 1 6. And then we will have to find the expected frequencies, and that's what I just showed you how to do. So the expected frequencies are the mean counts that would occur if the null were true. So if it met our expected distribution, and how we find it is if we have our probabilities P1, P2, and N is the total number of trials or the sample size, we multiply N times P1 to get each of the expected frequencies, just like I did here. I took the percentage times the sample size, and that's how I get my expected. If they do not tell you the probability, or they say it's uniform, so if no probabilities are given, we take the sample size and we divide by the number of categories, and that will give me the count. Will give me the expected counts for each one. And then what we'll do is when we run the test, we're going to get the chi-squared statistic. This statistic measures how large the difference between the observed and the expected, and it's called the chi-squared distribution, chi-squared statistic. So if K is the number of categories, and we have observed 1 through observed K, and then we have our expected frequencies through expected K, what we find out is the chi-squared statistic is we take the observed minus the expected, we square it, we divide by the expected, and then we add them all up, and that's how we get the chi-squared value. And the one assumption for this test is the expected counts have to be at least 5. We don't have expected counts at least 5. We don't have enough observational data to do this study. So you have to have at least 5 in each category. So when I do my test and I find my expected, I need to check that all of these are greater than or equal to 5. If not, there's not enough data in that category for this test to work. So how we do the test will depend on the type of calculator you have. So I'm going to have 2 different videos based on the type of calculator, one for a newer calculator and one for an older calculator. So if you have an older calculator, and if you go to that test and you scroll down to D, chi-squared GOF test. If you do not have that command, then you're going to watch my older calculator video on how to run it. If you do have that command, then you'll watch like for the TI-84 plus video, right? And so I will have another video on how to do the test and separate it by the type of calculator you have. So please watch then the next one after this to know how to run the test.